Deterministic multilayer models of globular star clusters. Content: introductions, the basic principles and relationships of the construction of multilayer structures, the evolution of the 5-layer structures, some details of the evolution of the globular cluster models, summary and conclusions. References: globular star clusters are spherical or somewhat flattened and contain from tens to 1,000 to a million stars. There are also dwarf spheroidal galaxies. The nuclei of galaxies and their surrounding halos also have a spherical shape, so the spherical form of stellar associations is their very common organization. Different ways of modeling star cluster are used. In some of them, the entire cluster area is considered as a continuous medium, in others as a set of objects with random kinematic characteristics. These models are not deterministic. In deterministic models, each body has its own size, mass, coordinates, and velocity. The gravitational interaction of each such body with each other body is investigated. Therefore, the position and velocity of the body are known at any time. In many works on solving the n-body problems, it is not that there is only one exact solution to this problem for the two-body problem. An exact solution of this problem is needed to test a computer program for its numerical solution. In reality, these solutions do exist. We have obtained several of them. For example, one for n bodies axisymmetrically located on the plane. In the second solution, there are two concentric layers around the central body, each of which contains n3 bodies. In this case, the mass of the body in each layer is different, and the whole structure as whole rotates around its axis. A multi-layer structure is created from the number of single-layer structures. In a single-layer structure, there are n3 peripheral bodies with mass m1, which are located axisymmetrically around the central body with then the body m2 together with the other m3, m4 and so on bodies rotates in the x1 y1 plane at an angle delta psi from the first body. Then, around the x2 axis passing through the second body m2, the entire plane with the bodies m2 and so on is rotated by at angle delta theta from the initial plane. The velocity vectors of these bodies are also located in the new plane. Such process of rotation through angles is performed subsequently for all bodies from m3 to mn3. Additionally, there are not bodies mi, but pericenters of their orbit pci on the initial circle, see figure 3b, and each body is at an angular distance phi 0I from its pericenter pci. As a result, a spatially distributed structure is formed, in which the coordinates and velocity of the bodies, due to their interactions, allow them to move in space with periods almost the same as in the plane. It is possible to create various spherical structures by various of angles delta psi and delta theta. So when creating each layer, the bodies are rotated 3 times by angles delta psi, delta theta, if phi 0i. In addition to these 3 rotations, 3 more operations are performed. Algorithms for all full rotation and 2 operations are described in works, and the multilayer structure 2 full program was developed based on them to create a multilayer structure. With the help of the program, a structure is created in which the bodies in layers are organized in certain order, one of which is shown in figure 40a. Then the n-body problem is solved using the Galactica program, which we have developed. After the interaction of the bodies for some time, the bodies will be evenly distributed over space. In this case, some bodies can collide and merge with each other, and while others can eject from the structures, then the stationary existence of the structure comes and its shape does not change. The most common program for solving the n-body problem are the programs n-body 2 and n-body 6 created by RSets. In these programs, for example n-body 6, the Hermite method is used based on the expansion of coordinates and velocity in a Taylor series. In this case, 3 derivatives are used. The Galactica program uses a high precision method of solution. Also, as in the n-body 6 program, the coordinates and velocities are expanded into a Taylor series, but derivatives with respect to the sixth inclusive are used. Galactica system is freely available on this site. Figure 5a shows the structure at the moment t equals 0, i.e. after its formation by the program Multilayer spherical structure 2. The segments show the velocity vectors of the second body, i.e. first body of the first layer, and the 1488 body, i.e. the last body of first layer. The structure has number of bodies in the first layer 99 and in the last layer 495. This structure is a model of a globular star cluster with the mass of one star is equal a half mass of the Sun. The mass of central body equal 4,901 mass of the Sun. Semi-axis of the orbit of the outer layer equal 1 parsec. The period of revolution of the stars of the first layer is 100,000 years. As a result of solving of n-body problem by the program Galactica, obtained the structure in figure 5b. It shows the structure at the moment 196 revolution of the body of the first layer. There were 46 collisions in the structure. On figure 5c shows the distribution of relative distance of bodies RR1 from the center of mass depending on these numbers k. The collision dynamics of the structure are shown in figure 5d. 40 bodies with double mass and 3 bodies with triplet mass have formed in it. the motion trajectories of bodies of different layers were studied. The studies were carried out for 2 time intervals, initial t equal 0 to 0.15 and final t equal 1.81 to 2.11. At the initial stage, the trajectories of body 2, 401 and 1488 differ little from a circle, and the trajectory of body 1434 immediately becomes elliptical due to the approach to the body 1311 at a distance equal to 90 body radii. On finite time interval, the orbit of body 2 decreases while that of body 401 increases. It can be seen from the 3D views of the trajectories that they can rotate in space, i.e. processes. As a result of the approach of bodies, the trajectories may change, the periods of revolution may increase or decrease. Next, consider the movement of bodies using example of thin layer structure. In first case, after the creation of structure, which consisted of 99 peripheral bodies, and in second, after the end its formation, which consisted of 994 bodies. One of the bodies was ejected into an elongated elliptical orbit. Such studies were also carried out for structures with 10 and 15 layers. Each body has its own peculiarity in motion, but all move in orbits around the central body with periods that may be close to the initial one, but may be more or less. But of the bodies, when approach other bodies, acquire greater velocity and is ejected from the structure. For example, 14 bodies with an initial mass of my1 and 3 bodies with twice the mass were ejected from the 10-layer structure. Structures with 10, 15, 24 and 34 layers were considered. The number of bodies then reached 30,000. The evolution of the first 2 was studied. When the bodies merge, they heat up and begin to rotate. Some of the bodies are combined into stable structure, i.e. constellations. The bodies in which revolve around a common center of mass. The number of such constellations, the number of bodies in them, and the periods of their circulation are investigated. Table lists the parameters of globular clusters which are modeled by the considered multilayer structures. The number of N2 layers varied from 5 to 34. The number of stars N in them varied from 1.5 thousand to 30,000. The initial outer radius of globular cluster AN2 varies from 1 to 6.8 parsec. The initial revolution period of stars in the first layer P1 took took two values, this and this, million years, while in the last layer P and 2 varied from 1.247 to 12.68 million years. The relative motion of stars in two constellations in a 10-layer structure was investigated. In one of them, this body revolved with a period of 388,000 years around this body with a double mass, and in other constellations with bodies such body and such, the circulation period was 37,000 years. This difference in periods is due to the differences in the semi-axis of their orbit. Table 1 lists the largest rotation period of stars, PRT1. They are equal to thousandths of a day. During such periods of rotation, stars can be destroyed, but for most stars, the rotation period are 2-3 orders of the magnitude larger. The average temperature of the merged stars is calculated using the heat capacity of water. For a central body, the temperature delta T0 is small, but for stars it can reach tens of thousands of degrees. This is the maximum temperature, but for most stars the temperature is 1-2 orders of magnitude lower. Published works on modeling globular cluster as a rule consider the evolution of the cluster shape, while the above features of the motion of stars in cluster are not studied. This does not allow making the method used in them. A method has been developed for constructing deterministic models of globular star cluster in the form of multilayer spherical structures. Their evolution can be studied, and the process occurring in them has been identified. The multi-layer structure 2exe program for creative structure programs for their analysis, and the structure file mentioned here are available at this site. The developed method for construction models of globular cluster has confirmed its efficiency. This method can be used to create models of both globular clusters and large stellar associations. The galactic system makes it possible to study the evolution of clusters and to investigate in detail the mechanisms of stellar interaction in them. References. Thank you for your attention.